Last week, we presented foundation and excavation issue, and this week we will present the design process and construction method of the core. I'll briefly summarize the contents of last week and move on. The Petronas Twin Towers are originally planned at Selangor Top Club and its horse racing track in Kuala Lumpur. The site is located at the contact boundary of two different formations, those of Canny Hill Formation and Kuala Lumpur Limestone. The geological condition of Kuala Lumpur limestone had constructive problem. When drilling, the bedrock irregularity of the site were identified. It was found that the bedrock elevation at the initial tower location varied so greatly. This made control of differential settlement impractical. Finally, the plan of towers moved 60 meters southeast toward Canny Hill. A series of interbedded shale, peelite, sandstone, and quartzite make a problem of foundation for high-rise structures, because each tower would expert 1,140 kilopascal, more than twice weight bearing capacity of Canny soils. A pile left consisting of friction pile location in Canny Formation were above limestone, but with the cavities and slump zone ground filled, with the pile length varied to minimize differential settlement. As a result of more than 200 ground surveys, a number of voids occurred in the limestone layer, and the Barrett method was used to excavate the underground continuous wall construction equipment and carry out basic construction. Friction between work and sand was augmented by injecting grout, a mixture of sand cement that had already entered. The embedded pipe installed on the outside of the fire surface. Eventually, each foundation was constructed with a mat layer on the top of Barrett, and the foundation was completed. In determining the structural system of the core, consideration was made for the usability of residents, the cost of construction, the conformity of construction, and the ease of supply of nearby areas, and 5 systems were proposed. The rest of system was inadequate for vibration damping and wind load test analysis. In the end, concrete base, compounding concrete circular tube, and steel frame slab was chosen. The system was consisted 16 columns and casting plates reinforced concrete core. The concrete inherent heaviness and effective for vibration damping and suitable for wind. In the end, the system solved difficulties of the 450-meter skyscraper by taking advantage of the steel and concrete. The core used double-deck elevator system. The system is vertical transportation system for high-rise tower. 58 of the 76 elevators were installed in 2 towers as double-deck elevator. One deck could carry 26 people, so it carried 52 people at a speed of 3.5 to 7 meters per second. It makes better use of the core space and requires less room for hoisting, thus maximizing the efficiency of passenger transportation. Tube-in-tube, which is also called as soft tube, is a coupled structure system by soft outer tube around the exterior and the stiff inner core. By using this stiffness difference of outer and inner tube, They resist lateral load such as earthquake and wind. In between the outer tube and inner tube, concrete beams are also used to connect them. Steel frame is placed on the concrete beam. The intersection wall of the 23 meter by 23 meter size concrete core contributed greatly to lateral stiffness due to the lack of opening. The formwork system used to construct Petronas Twin Tower is hydraulic self-climbing formwork, which is also known as jumping formwork. Hydraulic self-climbing formwork is very efficient in concrete casting, as in an average of one floor can be completed in 4 days, which is a lot quicker as compared to the conventional formwork, resulting in speedy construction time, which used only 6 years to complete the project. In order to reduce the construction time, the German high-pressure pump was directly pushed up to 381 meters, exceeding Hong Kong Central Plaza's 306.5 meter record. This technique is used constructing of inner tube core. The construction sequence of self-climbing form is as follows. First, erect the formwork, install a ball bracket and use cone suspension and lateral bracing to secure the formwork. Place the reinforced bar in position. Then commence the first section of concrete pouring. Second, dismantle the formwork and install the anchor shoe, lifting up wall bracket and formwork, then install the middle platform. Adjust the formwork to the right position and commence on the second section of concrete pouring. Third, jack the formwork system and wall brackets to the next level and attach the hydraulic system, guardrail, and suspended platform. Fourth, close formwork and tighten it. Then commence on the third section of concrete pouring. Fifth, dismantle the formwork and move it backward. Attach it on the wall and the climb rail. Then close the formwork and tighten. Sixth, commence on the concrete pouring. Seventh, repeat steps 3 to 6 until the required level of the wall has been reached. Generally, jump form system comprises the formwork and working platforms for cleaning and fixing the platform, steel fixing and concreting. The formwork surface itself on the concrete cast earlier, so doesn't rely on support or access from other parts of the building. Jump form systems are suitable for construction of vertical concrete elements in high-rise structure, such as core wall, lift shaft, stair shaft, and bridge pier. Jump form systems are typically used on buildings of 5 stories or more. Fully self-climbing are generally used on structures within more than 20 floors. However, a combination of crane-handled and self-climbing systems can be viable on lower structure. The benefits of using climbing formwork as follow. They usually don't require a crane to move them. Increased construction speed is obtained by allowing the vertical and horizontal part of building to be built concurrently. It doesn't need additional support to the formwork. High-quality surface finishes can be achieved, can sustain high wind. The formwork system is easy to clean and reuse, with little formwork waste generated compared to the traditional formwork. The reduced use of scaffolding and temporary work platform result in less congestion on site.